Hello, everybody, and welcome to today's webinar presentation, Scaling Kubernetes with Splunk and Google Cloud, brought to you by Splunk and Google Cloud. I'd like to introduce you to our presenters, Amit Sharma from Splunk and Brian Farnham from Google Cloud. And with that, I will pass it off to the presenters.
Thank you. And welcome again, everybody, to this webinar, Scaling Kubernetes with Splunk and Google Cloud. Let's get started. So the obligatory legal slide, we might be making forward-looking statements. So we advise you not to make your purchasing decision based on just this presentation alone. So a little bit about myself. I do product marketing at Splunk. Before Splunk, I was at SignalFX, and SignalFX is the real-time cloud monitoring company that Splunk acquired almost about 2 years ago. Before SignalFX, I was in the same role at FD and Cisco in container networking and monitoring products. So I have had quite a bit of experience in monitoring and observability space, but I started my career, and majority of my career has been in software engineering. And we are delighted to have Brian from Google Cloud. Brian, do you want to introduce yourself?
Sure, thanks, Amit. So my name's Brian Farnham. I am currently a customer engineer as more publicly known, a sales engineer at Google Cloud. I am responsible for the Sell With partnership with Splunk, so I do work with Amit and his colleagues at Splunk a lot to help people on their journey with Splunk on Google Cloud. Before this, most of my career was spent at Cisco in the networking space. I did both technical marketing and sales for the data center side of the business.
Perfect. Thank you, Brian. Thanks. We are glad that you are here today. So today, Brian and I are going to talk about the state of Kubernetes adoption, why customers are adopting Kubernetes. And Kubernetes is not a binary event, it's a journey. And what are some of the operational challenges when our customers, in our interactions with customers, when they adopt distributed systems such as Kubernetes, what are the operational challenges that they encounter? And then we will get into why GKE. There are over 600 or a lot of Kubernetes implementation. If you go to CNCF, there are tons of Kubernetes implementation. So why we should pick GKE. And then we will get into a real-time monitoring and troubleshooting at scale. We will have a demo where we will show you some of the real-world performance issues and how to solve those challenges and how to troubleshoot and triage those real-world performance issues with Splunk. And we will have enough time for Q&A as well. So Kubernetes adoption is continuing to grow. It is the default de facto standard for container orchestration. So the net of these numbers is, I especially like the last one, 92% of enterprises in our latest 2020 CNCF survey say that they are using Kubernetes in production. Now that's a self-selected crowd because people who are going to KubeCon, they are adopting Kubernetes. But in general, analysts are finding that their clients are adopting Kubernetes in production. At Splunk, we have tens of thousands of customers. What we are seeing as Kubernetes is now approaching like one of the biggest source of data ingestion at Splunk. Not only that, what we are seeing is the number of containers are increasing in production and the high density of containers per node. Right? So the bin packing companies are starting to realize the benefits of bin packing. So Kubernetes is continuing to grow at an astonishing pace. Now, why customers are adopting Kubernetes? The primary reason is the agility, the speed. It makes software delivery, the shipment of software faster. This means that speed is paramount in all parts in the software lifecycle, and our customers, companies in general, are utilizing Kubernetes to ship code faster. Second is operational efficiency. Now, it is easy to scale your applications both up or down with Kubernetes. Now, Kubernetes gives you a way to have the desired state and it is continuously monitoring your current state of the system. And it is triangulating with the current state with the desired state. And at any time there is a gap, it will take corrective action. For example, if a node goes down, it will try to restart using the auto-scaling policy to bring back another node. A pod goes down, it will restart the pod. The end result is that your DevOps teams are a lot more efficient and more productive. And finally, we talked about the bin packing, the cost optimization. Now, using Kubernetes, companies are utilizing their infrastructure better because of higher container density. They can get so much more from their existing investment in infrastructure. So if that is true, why every single workload in every company is not on Kubernetes yet? Well, there are operational challenges. Now, complexity, security, monitoring are some of the top challenges. Monitoring is interesting for us. 32% of companies say that monitoring is one of the biggest inhibitor or challenge as they start to adopt containers. Now, really interesting is that challenge grows to 48% of enterprises are saying it is a bigger challenge as the scale of that company, as the size of that company grows in terms of number of employees or revenue. Now, that's kind of intuitive because the bigger the company, the more diverse workloads they might have. They may have more number of workloads, period. And distributed nature and diversity of workloads creates complexity, and monitoring those workloads, hybrid workloads from one place becomes a bigger challenge. The scalability is a big challenge. When you are looking at scaling Kubernetes cluster, you not only have to think about your worker nodes, but also the control plane side, unless you are using managed Kubernetes implementation such as GKE. You just don't have to deploy your application and that's it, right? So in reality, you are deploying a lot of other objects, other Kubernetes components on the back end, such as load balancer or services. The scalability of your application is actually multi-dimensional in Kubernetes. You will have to account for things like how many nodes can you run in a cluster, which in itself is complex. The number of pods per node, how many namespaces you're running, how are you isolating your services, how many services you're running. In Kubernetes, you will have higher churn of your pods and containers. There is a saying that treat your clusters like cattle, not pets. And Kubernetes does that for you. So in case a pod or a container dies, it'll restart. But this means in monitoring is much harder as your system needs to be able to keep up and give you the right results at the right time, in real time. So just to start a simple pod, as you are seeing in this diagram, there are a whole bunch of Kubernetes objects being created, and that is a distributed nature of Kubernetes, sometimes 50 or 60. And all this data is coming at you from all these different components. So high cardinality of data becomes an issue. So traditional monitoring tools are not able to handle this ephemerality or dynamic nature at scale of Kubernetes. So we're going to talk about that in a few minutes. But speaking of scale and how do you scale distributed systems, we have Brian from Google, and Google knows a thing or two about scalability. So Brian, take it away.
Thanks, Amit. I wanted to start off with an example that's kind of relatable to anyone. So back in 2018, Google did one of their doodles for Halloween. And this wasn't just a picture or an animation, but it was an actual game where people could play it within their browser. And this was all run on containers in Google Kubernetes Engine. So I wanted to show this and the scale that we ran at. So this game was only online for 65 hours total. In that 65 hours, we had 100 million players across 62 countries. And at the peak, we had about 500,000 of concurrent users. So looking at our Halloween example, you can see at the scale that we kind of run at. Overall, as a company, Google does spin up 4 billion containers per week. This amounts to about 6,600 containers every second. And this is because we have a lot of products that have a lot of users. So we have 9 products listed here with over 1 billion users each. If you look at Google Cloud itself or Workspaces as a product itself, those would probably add to this as well. So as you can imagine, Google had to figure out how to run such a vast system at such a vast scale. So back in 2003, you can see on this timeline, Google invented something that we call Borg. This replaced a batch-oriented system and a service-oriented system and kind of unified them. There was another back-end system called Omega. We merged the two of those together, and then that's what we have, as you know, today as Borg or Kubernetes. In 2014, Google open sourced Kubernetes, and we've now had it on Google Cloud for over 6 years, bringing the power of this to all of our customers. This enables customers to scale to massive workloads, not worry as much about control plane issues and running a control plane and configuring it. The Halloween doodle I mentioned earlier actually ran on GKE or Google's Kubernetes engine. It wasn't some internal service on some internal thing. So we were able to use the same thing that we give you, our customers, to run something that ran for over 100 million players. Later on, if you look at this timeline here, we have Anthos. That's our Kubernetes for multi-cloud or hybrid cloud. We won't get into that much here. But the last thing that we launched early this year, GKE Autopilot, I will touch on later in this presentation. So taking a look back at the Halloween doodle from 2018, this is a screenshot of it running in GKE just on Google Cloud Platform, showing what we did. So what you can see here is we had Kubernetes clusters in many geos across the world, and we ran the different clusters to scale up and down based on whatever needs were there at the time. So we didn't have to run this internally. It wasn't some special system. What we did is we used what we give our customers, and we're able to run that at a scale. So when we're talking about containers and Kubernetes as the management system here, people ask, what is the easy part? What is the hard part? What is Google really giving me? And why shouldn't I just do this on my own? Well, installing and managing your own cluster is the hard part. There is a book written on this. It's called Kubernetes the Hard Way. It is a good read. It takes a long time to set this up if you want to try it. I've been told it's about a week to do so. So you're more than welcome. Maybe you should do this if it's a journey that you need to take. But when you're loading an application or spinning up an application in containers, there's a lot more things that you have to do behind the scenes that GKE can help with. You know, provisioning the machine, the runtime, configuring the network, cluster services like monitoring, logging, and DNS, setting up the load balancers as well. And once you've set all this up, now your work's not over. You actually have to do day 2 type operations, right? You have to do your updates and you have to scale your cluster. So what we're trying to do is give you Kubernetes in a much easier manner, which I will show you now. So as I've mentioned, GKE is the way to run and scale your application without having to worry about all of those underlying systems. The control plane's taken care for you, and you can get a Kubernetes cluster up within a few minutes. This allows you to get your business focused on its business value and not worrying about all of those little things that aren't the drivers of your revenue. As you can see in the screenshot here, this is the GUI version of setting up a quick Kubernetes cluster. You only have to input the name, whether you want it to be zonal or regional, which zone if you choose zonal, and which region if you do choose a region, what version, and the machine types you need, and then you're off and running. One question we do get about GKE, and it comes up pretty often, is, all right, you've set up all of this stuff and run it behind the scenes for me, but how do I know it's secure? What's going on? What features do you have? In today's world, security is obviously paramount, so I did want to go over a few of these things with you. We help you from the beginning operate any Kubernetes cluster in a secure manner, and as you do scale, this generally gets harder, right? So we want to start you off with that secure foundation. There's certain things that we do, like a minimal OS. So it's not just making it smaller and more efficient. Maybe you can pack more things into a physical machine, but this also helps you mitigate any vulnerabilities as you're only running what you need to run. So you're not exposed to as much in that open world. auto upgrades of your clusters, your Kubernetes clusters. That helps you get your latest security patches, obviously, and we kind of do a running version of those, and we'll run 3 versions at once and upgrade you as you need. We have a sandbox, GKE sandbox there on the right side. That's for workload isolation. So this is isolation at the pod level, and the technology behind it is similar to what you might know when you talk about virtual machine hypervisors. And lastly, the one I'll talk about is the private clusters. You can fully run this on private IPs and restrict access, so only your master nodes can touch it. So these clusters are truly private, and this obviously keeps out the outside world for the clusters that can use that. And now that we've talked about the secure aspect of it, I want to come back to something I showed on the timeline earlier in the presentation. So GKE Autopilot is actually an even more automated version of your Kubernetes cluster that's for you. It's something we introduced more recently, and it's something that we're seeing great adoption on. So what this is reducing your day 2 operations, your upgrades, your patches, things like that. What you do is you make Google your SRE. It's still Kubernetes, and we're not changing any of that, but it is something to help you with that day 2. So I've mentioned Autopilot, and I've talked about the normal Kubernetes mode of operation within Google Cloud. And what I want to show here is kind of those 2 modes of operation. We realize some customers need more control over their clusters and can't do Autopilot. And that's where these modes of operation come into play. The mode of operation can be explained as the level of control that you need to have over a given cluster. And you can choose. The mode of operation can be mix and match mode of operations between different clusters as well. So we're trying to be as flexible as possible there. But basically the 2 modes here we have are GKE Standard and GKE Autopilot. With GKE Standard, you have the advanced configuration flexibility over that infrastructure. And with GKE Autopilot, Google will provision and manage the entire cluster and its underlying infrastructure for you. You as a user are in full control and can break glass. You can convert Autopilot clusters into Standard, and in the future, will enable migration in the opposite direction, from Standard all the way over to Autopilot. So I wanted to go a little deeper into the GKE Autopilot mode of operation. This is a new mode of operation within GKE, as I mentioned before, and it manages your entire Kubernetes cluster's infrastructure, control plane, node pools, nodes. It does a lot for you. Autopilot is fully managed cluster, bringing together the best of our GKE advances in scaling, security, and day 2 operations into a Google SRE managed and optimized Kubernetes cluster. When you use Autopilot, Google continues to innovate and continues to be a leader in the container orchestration space, and we offer a complete end-to-end hands-off Kubernetes experience. It's making it a lot easier for you, right? You don't have to worry about all of this, and you worry more on your application. When you let Google manage the entire cluster, we manage and monitor all operational aspects of the cluster, the control plane, the worker nodes, the core Kubernetes system components, and we ensure your workloads always have a place to run and are running efficiently. With that, I did want to hand it over to Amit to talk about monitoring all of this. As you can imagine, and as we have both mentioned, once you get to this level of scale, you need to know what's going on. You need to know what's happening in your system, and we want to make sure that there's a great way for you to do that.
Thanks, Brian. So before we talk about how does Splunk help you with triaging and troubleshooting performance issues in Kubernetes environments, let's understand why monitoring in Kubernetes is challenging. Well, first off, it's just more number of components. Traditionally, you had a physical server, and then you have your applications deployed on top of it. But now you have physical server, then your guest operating system, host operating system, your container runtime like Docker or Cryo or Containerd. You have Kubernetes platform itself. Then you have microservices running on top of it, which may need storage or networking interfaces that you have. So there are just many more layers and many more number of components in the tech stack. Second, these components are dynamic. They are ephemeral in nature. Now, traditional tools struggle with the dynamism or ephemerality. So what I mean by that is some of our customers are, when they push a new code, new release, they use immutable infrastructure. That is, they take out everything that they had in a previous deployment, and everything about the infrastructure restarts from scratch. So some of our customers are starting like 50,000 or even more containers from scratch. So that creates challenges for traditional monitoring tools. Then you have multiple data sources. You have metrics, events, logs, traces, and DevOps and SRE teams constantly switch context among these monitoring tools. And not only just the Kubernetes, and again, as I mentioned, Kubernetes is not a binary event. You may have workloads running on your on-premises data center or on just cloud like a virtual machine or on your private cloud. So these different data sources are reporting from different sources, from different applications. So understanding all of your applications from one single solution is important. And finally, lack of automation. So if this data is coming at you from a variety of sources at a high volume and at a high velocity, just making sense of this manually is no longer sustainable or no longer possible. So you have to use AI or machine learning or data science enabled technologies to make sense for you. So a new approach is needed for observability in Kubernetes. And starting from the bottom is you need to understand the entirety of Kubernetes clusters, the health and performance across the entire clusters or multiple clusters. Now you need visibility into interdependent components. As we will see, there are different components in Kubernetes, the nodes, pods, containers, workloads. How are they related to each other, and how each performance is going to impact the performance and health of the other component. Then you need granular logging and logging within context. Streaming analytics and real-time alerting give you insights in real time as things are happening so that you can take action or you can automate. And that is the final point. You can automate responses in real time. And don't just take our word for it. Gartner advises thousands of clients who are adopting Kubernetes and containers, and they wrote a report on best practices for Kubernetes and containers in production. So this real nugget from that report is their recommendation is to favor tools that have granular logging, supply automated service discovery, and can provide action-oriented recommendations in real time using analytics and or machine learning. By the way, this report is in its entirety is available from Splunk. So I want to talk to you about Kubernetes Navigator, which is real-time observability for containerized deployments. Now, this is not a product; it is a feature. It is a capability within Splunk infrastructure monitoring, and Splunk infrastructure monitoring then integrates with Splunk core to provide logs in context. Splunk infrastructure monitoring itself is a metrics-based platform that provides real-time insights about what's happening in your Kubernetes cluster. So we're going to talk about these capabilities and the outcomes that it provides for you, and then we will see them in action in the demo. Starting with the installation and configuration of the data ingestion. So it is a one-step Helm installation. So all that command is provided to you, specific to your Splunk infrastructure monitoring environment. Now, once the data starts to ingest within a Splunk infrastructure monitoring, it will automatically discover all the Kubernetes components, and not only just the Kubernetes components, but also the deployed applications. Things like Redis, Cassandra, Nginx, hundreds of these applications that you use every day. So it will automatically discover and provide pre-built curated dashboards for these integrations, and that provides the immediate value. You can look at the pre-created or pre-built dashboards, but also you can create customized dashboards and charts for your own environment within seconds. When you look at Kubernetes Navigator, the dynamic cluster map provides a bird's eye view. Now, it enables teams to quickly understand the performance of the entirety of Kubernetes environments. It provides intuitive and hierarchical navigation. So select, filter, or search for any Kubernetes component or entity. That is node, pod, container. You can go into services, microservices that you have deployed, all that within seconds. Now, as we mentioned, the Splunk automatically discovers these components and the containerized services to instantly monitor your entirety of your stack. You can understand the relationship between these components and quickly fix any interdependent or performance issues that you may have within Kubernetes. Now, while a global at-a-glance view into the entirety of Kubernetes environments helps teams understand how the overall system is performing, it is equally important to have a granular, detailed view into individual components, as teams would need to narrow down the source of the problem. So drilling down from nodes to pods to containers to workloads, all this you can narrow down and you can drill deep into these components within seconds. And that is possible because of our streaming architecture. And we are going to talk about that in a couple of minutes. Now, as I mentioned before, Splunk infrastructure monitoring, you can seamlessly pivot to Splunk Core, Splunk Cloud, or Splunk Enterprise environments to get granular visibility into your application, Kubernetes, or container logs. And using that, you can correlate performance across the entirety of the stack without any context switching. This will give you visibility into lifecycle events of Kubernetes and the API server. And you can also look at the API server audit logs, and that can help you understand and maintain your security and compliance posture. To understand the why behind performance anomalies, Kubernetes Navigator leverages AI-driven analytics. Now, this automatically surfaces insights and recommendations to precisely answer in real time what is causing these anomalies across the entirety of cluster. So wherever it is happening, nodes, pods, containers, workloads, wherever that is occurring. Now, following suggested filters, SREs or DevOps teams can narrow down the underlying issue within minutes. I want to touch base here on our alerting capabilities. So sophisticated algorithms such as historical anomalies or sudden change can detect system-level issues, such as sudden increase in container restarts, and it can give you precise alerting within seconds. We talked about traditional monitoring tools which are based on batch and query of metrics are not suitable for monitoring cloud native and ephemeral environments such as Kubernetes. And here's the representation of that traditional batch-based metrics architecture. So what you're seeing in the middle is the time series database. So typically they would store metrics in time series database, and on the right-hand side of the screen, there are separate components, right? So we have analytics and visualizations, you have charts and dashboards, you have alerts, you have automation, data science. All these components periodically pull data from time series database and then they refresh their state. So that is why it takes that pulling and refreshing, it takes minutes, sometimes tens of minutes to give you insights. Next, I want to talk to you about why we built our real-time architecture and how it solves detection within seconds. So there's a lot of things going on in this slide. I want to first talk to you about why we built this way, why we built a real-time streaming architecture. And then I want to talk to you about how we achieve that capability. So why? Well, ultimately, monitoring is not just about putting up pretty charts on wall TV. Monitoring is putting yourself in a position to anticipate problems. Monitoring should really be about interactive visualization. You have all this data coming in from different components. Use that data to explore, query, and understand your system. You need real-time alerting, zero lag alerting, no unnecessary delays in getting you the information you need to know about things that are abnormal or trending abnormal. And then you have live data feed. Using that, you can automate all but the most trivial remediation workflows. You need to have insights that you can trust and up-to-date and accurate. You cannot wait for a batch processing to deliver a late result. And of course, now, if you're looking at the small amount of data in dev, test environments, you have all the time in the world. But as you're scaling your Kubernetes deployments, as you are getting into production and you are putting multiple workloads in Kubernetes, your monitoring and observability platform will have to scale as you scale. And then you need a system that will support it. And that's where Splunk comes in. And now let's talk about how we deliver the real-time capabilities. The way to read this slide is from left to right. So there are several patented innovations that we have developed on the promise of real-time. But the essence of what we are doing is streaming all the way through the system. So first, and again, as the data coming in, look at the very left of this and top of the slide. So first we separate out the metadata from the data value right at the front door. More importantly, it allows us to scale our systems to support different classes of data independently of one another, right? So metadata are like things like labels and properties and tags, like what application is that and which environment, dev, test, QA, pre-production, production, which cluster it belongs to, which region or availability zone is this running in. So there are many dimensions to for data in Kubernetes environments. So we can, by separating metadata from the data value, we can support high cardinality of the data that is coming into a system. Now, second, we dynamically adjust the jitter or lag that is inherent to any cloud system or any system that includes a network to ensure that our analytics is always accurate. Third, we put all the data into persistent data stores, but we optimize it for retrieval times so that the historical data can be used in analytics and visualization as quickly as the live data can. So you can do, this is the value of, this is the number of objects or widgets that I ship now. You can quickly see what was the value last year or 6 months or before I released the new build or new code. So you could do all these analytics in real time. And finally, we have analytics engine that subscribe to live data streams. So all the live data that is coming into the system is going through the entirety of the system, is streaming to the analytics engine, the dashboards, the alerts. So instead of batch and query, data is streamed to these systems. So your dashboard will refresh, your alerts will fire, your automation cast will trigger within seconds instead of minutes or tens of minutes. Now let's see the system, the product in action in our demo. All right, so in the demo, we are going to create a Kubernetes cluster on GKE. We will deploy the applications on the microservices-based applications on that cluster. And purposefully, we will create some errors, some performance anomalies in those applications. And then we will use a Splunk to detect those performance issues in real time within seconds, and then use the Splunk cloud environment to look at the logs that's coming in within context to triage and troubleshoot those performance issues.
So in the demo, I have 2-node Kubernetes cluster deployed on Google Kubernetes Engine, GKE. I'm calling this Kubernetes cluster GKE demo cluster. So what you're looking at in your screen is Splunk infrastructure monitoring, and that's the product. And you are looking at Kubernetes Navigator. Splunk infrastructure monitoring gives real-time visibility into your cloud infrastructure, your orchestration platforms such as Kubernetes, and hundreds of integrations, technologies that you use every day, things like Kafka, Redis, Cassandra, MongoDB, etc. So here we are looking at Kubernetes though. So we have a two-node Kubernetes cluster. So what you're looking at, two nodes, right? So this is one node, and we can take a look when we click on that magnifying glass on this node. This on the right-hand side, you have the performance characteristics of that node. So here you're looking at Kubernetes or the node. You are looking at visually everything is working fine. Node is ready. The smaller squares on this node, these are the pods that are deployed on this node. And this is a container within the pod. So here you have 4 containers running on this pod, and when you click on the pod, you are given more details on that pod. What are the performance numbers, CPU, memory, as well as what are the workloads that are deployed on this particular pod. You can click on a container, and here visually we are telling you the container is running, pod face is running, container is ready. And then on the right hand side, you're looking at the container performance characteristics, details on that. So this, you can navigate from hierarchical navigation from nodes to pods to containers to workloads. You could quickly look at workloads that are deployed on this cluster. So I have deployed an e-commerce application, and we will take a look at that applications in a little bit. But I have all these services that are running on that on this cluster. On you could take a look at like any object, for example, and then you can take a look. Again, the performance characteristics are here, but if more details are needed, you could go and get more details on that particular node. In this case, this is the node. These are the containers deployed on this node, CPU by pod, memory usage by pod, network in, network out, as well as what are the workloads that are deployed on this particular node. Now, what happens is this is like a simplified two-node cluster, but let's take a look when you have multiple clusters in your environment. Here I have tens of clusters running, and this particular, so every particular this is one cluster, and then so on and so forth, right? Multiple clusters are running. Let's take a look at this particular cluster. And again, as you can see visually, I can see these are this particular node. Some pods are working fine, right? Visually, you are seeing this particular pods on this node is working fine. This node is working fine, although some nodes are running into performance issues, such as memory pressure in this case, right? Certain nodes are running in memory pressure. So how do we figure out like what's happening? So in slides, we were talking about Kubernetes Analyzer. Kubernetes Analyzer is the AI-driven capability which is looking at the entirety of the cluster and seeing patterns. If there's anything common which is happening across your cluster. So to get to Kubernetes Analyzer, we get here. And again, the Kubernetes Analyzer function is looking at entirety of the cluster, like all the nodes and pods and workloads deployed. And it is seeing that there is something related to the high memory nodes. And that is service, which is deployed. It's called Autobot. And that is deployed, and it is causing high memory nodes. So let's just see what is happening on the service. So when we click, it gives us all the nodes on which the service is deployed. Now what you can see on this one, I have Autobot service running. However, it is also giving you the other neighboring containers and pods that are running. So what is happening is this commonly known as noisy neighbor issue. So this is the service in interest, Autobot, and these are some other services, some other pods that are running on that particular node. So let's pick a node such as this, and let's see what's happening. And this is the pod on which our Autobot service is running. right? So Autobot service is running the workload on this particular pod. Let's get more details on this particular pod. So again, these are the neighbors, and this is the service that we are investigating. There is this container which is running on the Autobot service pod. And let's take a look. Container is ready, but just by visually, we can see pretty much all the memory on this node, like 88%, 90% of memory is being consumed by this particular workload and or this particular container. And at some point of time, your neighbors, other workloads that are running on this node may run into out of memory. So let's take a look at why this is happening. And when we see the properties of this particular container or workload here, we can see that developer has forgotten to put a limit on memory. So this is consuming unlimited memory. And if there is a memory leak or if there's a huge consumption of memory, this particular container or workload will start consuming more and more memory, and other deployments on this particular node may run into issues. So you saw just in a couple of clicks, we can converge or we can find triage the root cause of what is happening, why this particular node is under memory pressure. So now let's take a look at this particular cluster that we have deployed. It's called GKE demo cluster. Now, as we were talking before, we have deployed an e-commerce application. Now, visually, we can see all the applications are working fine. This particular pod, on the other hand, is having issues. So it is called email service. Email service pod is having issue. So here we can do just kubectl get services. So again, these are the services deployed. This is a load balance service, which is a service object in Kubernetes. So let's take a look at this front end external service. So we have an external IP for that service. So let's go ahead and take a look and visit this web page. So this is an online boutique application. This is simple but not trivial. So it has multiple services written in different programming languages, and which is giving you this online e-commerce application. So you could search for an object, you can click on an object, you can add to cart. There's a product service, product inventory service, checkout service, and here we are checking out and placing the order. So this service is deployed on our Kubernetes cluster, and here what we are seeing is all these services are deployed. This particular service, which is sending email behind the scene once you check out a product, is having an issue. We can visually see there is something wrong because of that red rectangle. That container is having issues. So how do we troubleshoot it? We have found out that this particular service is telling us visually is having issue. You can also create an alert and it will alert you that there is something wrong, but we want to see what's happening here. What is the root cause? To do that, what we will do is we will click on these three dots, this option of examine in Splunk. So we can click on this and it will get to the logs in context. So here we come into Splunk cloud environment, and you saw I didn't have to type in any SPL or any context that is I need to provide. All the context is transferred from monitoring workflow to troubleshooting workflow within Splunk Cloud. So let's take a look what's happening. So here it is telling us back off restarting failed container. So as soon as Kubernetes is starting this application, it is getting into crashback loop of error. And that usually happens when there's something wrong with the application. So let's take a look at the workload itself. So we'll go to workloads and take a look at email service. And email service, again, we get to this on the right hand side, this panel, and we will do the same thing, examine in Splunk. Let's see if there is any issue with this particular service. And lo and behold, by the way, we are getting an error. And again, I did not have to type in any SPL or I had to search anything within Splunk. It is taking me to contextual logging. So I have some details on that particular service. And as you can see, there is some error that actually I introduced. So I added this error to simulate this condition. So there's this error on email server.py. It's a Python application on line 14. It is trying to get logger object. As soon as it gets it, it gets into the application, the runtime, Python runtime crashes, and it gets into crashback loop of status. So we saw again within a couple of clicks, we can see what is the problem and get into contextual logging and get to the root cause. We can take a screenshot of this and send it to our developers if we are SREs, or we can share this with our developers and they can fix the underlying root cause. So I want to share one more thing here. So I have deployed a workload. And let's take a look. It's a cron job. I call it hungry job. It's a cron job. It wakes up periodically and does its thing. Here it is just sending us hello from Kubernetes cluster. But what I did interestingly here is I'm requesting 50 core and 32 gigs of memory. So I deliberately I'm asking for so much more resources that my too little node Kubernetes cluster does not have. So what happens? This Kubernetes will not be able to schedule this pod. Now, when you get to Kubernetes Navigator, it is looking at entirety of cluster, and again we are looking at Kubernetes Analyzer, and it has seen this problem happening across the cluster. So it is telling us this workload hungry job is trying to schedule, Kubernetes trying to schedule, and it is not able to schedule this. And this is the condition related to pending status, pods with pending status. And it has tried 428 times so far, and it's not able to schedule this. So here in Splunk, we search for hungry job. And let's see what happens. So let's see. It is telling us the logs are telling us that 0 of 2 nodes available, insufficient CPU and insufficient memory, failed scheduling. So it was expected, but Kubernetes Navigator, the analyzer function, found out for us by looking at the entirety of Kubernetes cluster automatically and surfaced this insight for us that there is a workload named hungry job, and I've been trying to schedule this pod and have been failing for like more than 427 times now. So you may want to take a look at this particular workload within Splunk and see what is the root cause of this workload remaining in the pending status. So what we saw here is just within few clicks, we can monitor the workloads, the nodes, pods, all the infrastructure, as well as containers that are deployed, as well as the workloads with Splunk and Splunk infrastructure monitoring. So with that, we have come to the end of our presentation. Let's go back to slide.
With that, we have come to the end of this webinar. Thank you again so very much for joining. Thank you for your time. You can start, if you have not already on your Kubernetes journey, start with GKE. It's easy to try. It's free to try as well. So if you sign up for Google Cloud, you could start practicing your Kubernetes skills on GKE, as well as use Splunk infrastructure monitoring for monitoring your workloads and Kubernetes environments. Splunk infrastructure monitoring is also free to start with. So you can get a 14-day free trial from Splunk.com. Again, thank you so much for your time.
So we can take questions now if you have any. Lucy, do we see any questions?
Yeah, so I'm pulling it up right now. Looks like our first question is, can GKE run Kubernetes on premise data centers?
So I can take that one. This is Brian. So we definitely can run in a hybrid environment as well as on other clouds. There's a version or a product called Anthos, which is basically our hybrid and multi-cloud version of GKE. So what you get is a control plane within Google Cloud that will talk to your on-premise data center as well as a different cloud. And then your clusters, nodes, your actual workloads can be in any place, whether that's on-prem, Google Cloud, or another cloud.
Great. So, so just to add to that, so as you can run GKE wherever you want to, either cloud native GKE or hybrid mode with Anthos, you can also send data to Splunk Infrastructure Monitoring, which, by the way, is a SaaS service, but it can ingest data from wherever you are running Kubernetes. So if you're running Anthos on-premises data center, then you can send data in the same fashion as if you were running on GKE. So it can ingest data from anywhere that you are running Kubernetes. The Splunk, of course, the core logging product, there's a Splunk Enterprise product that you can run on premises if you want to, or on cloud environment, bring your license, or you can use a Splunk Cloud, which is a SaaS service from Splunk.
All right, and it looks like our next question is, do we have any free Splunk version to be used for hands-on Windows?
Yes, so you are looking at Splunk Enterprise, and you can download the free trial of Splunk software, Linux or Windows or Mac, from Splunk.com, or you can try as a fully featured, fully functional Splunk cloud environment, which is a SaaS service. That also you can try for free on Splunk.com.
All right, that's great. Our next question is, how can your solution provide application performance for the applications that are running on Kubernetes?
Yeah, so great question. So as you saw in the demo, it is providing the visibility into health and performance of workloads that are the applications that are running on the product with Splunk Infrastructure Monitoring, which is our metrics-based platform. And you also saw the application logs within context in Splunk cloud environment. So you can do triaging and troubleshooting of your application as well as visibility into their health using Splunk Infrastructure Monitoring and Splunk Cloud. However, to get granular details on distributed tracing, how applications are calling each other and what happens to a request when it comes to the front-end external service and how it propagates to different services that we showed in the demo. We have a product called Splunk APM, Splunk Application Performance Monitoring. So that can help with distributed tracing in your microservices-based environments.
All right, and our next question is there a scalability limitation on the number of nodes and clusters specifically with Splunk solutions?
Yeah, so I can talk about Splunk scalability of monitoring and troubleshooting, but Brian, do you want to take a moment to talk about GKE scalability?
Sure. So there's actually a lot of different parts to the scalability. I would suggest Googling GKE scalability, and there's a couple of guides there. It's within the first 3 links, you'll find it all. But we do have some larger scale numbers that I think are worth mentioning. So if you're on GKE 1.18 or later, we can actually run up to 15,000 nodes per cluster now. If you're on older versions, we're limited to a third of that, or 5,000 nodes. And then when we start talking about scalability in terms of putting things behind a service or a load balancer, there's some numbers there. Whether you're using a network load balancer, an external HTTP load balancer, internals, there's some different numbers there. Specifically for an external HTTPS load balancer, we got 1,000 nodes per zone. And there's some other nodes, scale numbers that you should be aware of. Each node, you can assign up to a /24 in terms of IPs for pods within that node, but that does limit you to 110 pods per node. As soon as you start assigning smaller subnets, you'll obviously get smaller there. But the /24 is kind of worth calling out because, if you're just purely from the networking world, that would be 256 IP options, but you're actually limited to about 110 physical actual pods in that node. So Google, that we have scale numbers posted for every product on GCP, and I would just put in the keywords GKE scale, and you should be able to find it pretty quickly.
Yeah, and just to extend the thought on networking. So not every pod will need a public IP. So you can actually run many more than 110 pods per node. What we are seeing on our end is our customers are just pushing the envelope, and they are deploying tens of thousands of nodes in a Kubernetes cluster, and thousands of nodes and tens of thousands of containers. So what we are seeing is not only the number of nodes is increasing, but number of containers within those nodes are increasing as well. So very high density, like a bin packing scenarios to get better infrastructure optimization or utilization, as well as that affects the infrastructure cost as well. So our customers are using thousands of nodes with the Kubernetes cluster with tens of thousands of container running. And Splunk infrastructure monitoring is built from the ground up to address the cloud native requirements, and the scalability within containers and in ephemeral environments such as Kubernetes is one of the key requirements. So it is handling all the scalability with high cardinality data because of this patented streaming architecture.
And I would say, to even add on to that, we have a overall limit in GCP today of 15,000 connected virtual machines within a single VPC network. So if you think about it that way, with GKE 1.18 and later, you can have 15,000 VMs, and then how many containers you can run per VM, you would obviously start scaling up pretty high pretty quickly there.
Very good. I think we are pretty much at the top of the hour. Lucy, any other questions, or can we wrap up the webinar?
Yeah, that looks like the end of the Q&A portion. So with that, DZone would like to thank Amit and Brian for a great presentation. DZone would also like to thank Google Cloud and Splunk for providing the audience with a fantastic webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career.